In this video, we will review normalization and then introduce anomalies that arise when a relation might not be sufficiently normalized. To review the things that we've talked about to this point, when we normalize, we do not look at the data. Sometimes data is provided as a way to visualize what is being stored and provide some context to the design, but we do not use data to decide whether a relation is normalized. I can always break your normalization if you let me add more data and you try to normalize intuitively. Do not normalize intuitively based on column headings or data. Normalize based on the mathematical relationships that we've provided. Bullet 2, normalize starting from 1NF. In other words, your relation must be in 1NF before it can be in 2NF. It must be in 2NF before it can be in 3NF. And do not be tempted to skip all the way to 3NF without validating 1NF and 2NF first. The things that we need to normalize in this class will be the relation. In this case, I typically use R to define the relation, and then in parentheses, a set, which is an unordered, unique list of items, a set of attributes typically represented by lowercase letters, separated by commas, candidate keys, which we don't need for 1NF, but we do need for, we do need for 1NF, my mistake, and then determinants and functional dependencies, which we do need for 2NF and 3NF. These things will be provided for you on an exam, or if you are creating an example for an assignment or just for your own amusement, you need to provide these things in your example. Provide the relation, provide all the candidate keys, provide all the determinants and functional dependencies. Then we can do the normalization that we need to do in this class. Here's a practice exercise for us to discuss. We're going to take this relation, this candidate key, and these functional dependencies, and we're going to go to 3F. Note that we cannot add functional dependencies as we go along. Those are the ones that we have, those are the ones that we have to use. So don't assume that there are some missing that should be in this list that aren't. If they're not in this list, then they do not exist. Don't use your intuition to try to create more FDs than are given to you. Solving our example, is it in 1NF? Well, if you refer back to the previous slide, it is, because there is a candidate key. I gave you A as the candidate key. There are no repeating columns because I didn't subscript any of the columns B or C and repeat them. And the columns are atomic because they are not composed of multiple letters. Since we have 1NF, we can now consider the possibility that this relation might be in 2NF. And immediately we realize it is not in 2NF because we have an attribute D that is not determined by the candidate key A. And the way you fix that is to decompose that relation into two relations. If it helps, you can think of normalization, the process of normalization, as attributes becoming relations or attributes being broken out of a relation into a new relation. In this case, our new relation is R1, and it contains nothing but that little orphan attribute that was not determined by the candidate key. It has no place to go, so we will put it into its own relation. We will arbitrarily say that D is the candidate key for R1 because we don't have anything else. And in order to be in 1NF, we need a candidate key. We will say then that D is a candidate key. We will say there are no functional dependencies, and mathematically there can be none because there is only one attribute in the R1 table. And then peeking backwards, our original relation R now has no D in it. It still has the same candidate key. It still has the same determinants and functional dependencies. A determines B, A determines C. Nothing has changed there. We just took out the D attribute. And those two look fine. We're not finished. We have to go back and check and verify that all of the relations are in whatever normal form we need, in this case 2. You can't stop here. You can't simply say, because I made a new relation and edited the original relation, then everything is fine. You have to go back and prove, you have to go back and demonstrate that R and R1, the new version of R and the new R1, are in 2NF. That's trivial to do, but you have to do it, and it would become more complex as we went to higher normal forms. We can see that R is in 2NF because all non-key attributes depend on the all candidate keys, and it's even in 3NF because there are no non-key dependencies. And if we take a step back to the previous slide to review R1, we can see that it is in 3NF because it is in 1NF because it has a candidate key. All the columns are atomic. There are no repeating columns. It is in 2NF because there are no non-key determinants, non-key functional dependencies. And we can see it is in 3NF because, well, there's only one attribute, and it's the candidate key, so there can't be any transitive dependencies or non-key dependencies. Here's a practice exercise for you. You should pause the video here, get yourself a bag of Fritos, a piece of paper, and a writing device, and solve this logical design to 3NF. I've given you all the functional dependencies. How do you know I've given you all the functional dependencies? Because I'm telling you these are all the functional dependencies. And it's easy to believe that when we're using A, B, C, D, and E for the attributes, because there's no intuition you can force onto this design. When we start adding column headings with semantic value, name, address, phone number, social security number, then it becomes a problem because your intuition wants to kick in and say, oh, there must be another functional dependency between column social security number and column address, column blood type, whatever. But don't do that. Go by what you're given. Use the functional dependencies and the determinants you're given. Use the keys that you're given. And do not normalize by semantics. Do not normalize by data. I'm going to move on to the next slide now. Hopefully you've got the solution for this worked out. Is it in 1NF? Well, yes. There's a candidate key, which is A. There are no repeating columns because I didn't subscript any of the columns and repeat the attribute letters. And all the columns are atomic because they're single letters and they cannot be broken down into smaller parts. We know we're in 1NF. Are we in 2NF? The rule is that all non-prime attributes must be dependent on all the candidate keys. The non-prime attributes are B, C, D, and E. They are non-prime because by definition they do not participate in any candidate key. B, C, D, E are non-prime. A is prime. To be in 2NF, all the non-prime attributes must be dependent on all the candidate keys, and that is indeed the case. We have one candidate key A, and all the non-prime attributes B, C, D, and E are dependent on A. A determines B, A determines C, A determines D, A determines E. Is it in 3NF? No, because I snuck in a functional dependency. I made C a determinant because C determines D, and that violates the 3NF rule. A non-prime attribute determines a non-prime attribute. The way you fix it again is you decompose the original relationship into two relationships, but instead of bringing down D all by its lonesome, we bring down C and D, and C becomes the candidate key because C determines D. And then back in the original relation, we drop out that poor little D that was the object of C, and we're left with A, B, C, and E. Notice also, as I have observed here, no new functional dependencies have been created. C still determines D, and A determines D is not lost because it's transitive. Since I have A determines C, I have C determines D, I can say A determines D. That is a transitive dependency. That transitive dependency is perfectly fine because it crosses between relations. In the first relation, A determines C. In the second relation, C determines D. And then if you combine those two together, you can assume that A determines D, which is perfectly fine across two relations, R1 and R2. R and R1. Are we finished? No, we're not finished. Dun dun dun. We have to verify that our new relations are in our desired normal form. And since we're after 3NF, we have to consider R and R1. Are they in 3NF? R1 is pretty easy. A candidate key, yes. Atomic columns, yes. Repeating columns, no. So it's in 1NF. Any non-key attributes not dependent on the candidate key? No. Everything's dependent on C. And then in 3NF, are there any non-key attributes determining non-key attributes? No. That means we are in 3NF. In the second relation, are we in 1NF? Yes, because there is a candidate key. There are no non-atomic attributes. There are no repeating columns. Is it in 2NF? Yes, because every non-prime attribute, every non-key attribute is dependent on all the candidate keys. Everything's dependent on A. There's no little orphans hanging out there. Is it in 3NF? Yes, because there are no non-key, non-prime attributes determining non-prime attributes. Those two are pretty easy. Moving on, let's discuss some anomalies that can be created if we do not normalize. And remember, there are other anomalies, but we are not normalizing beyond 3NF. Therefore, we will just discuss anomalies that we may encounter in 1NF, 2NF, and 3NF. So don't worry about other anomalies that you see in the data or other anomalies that you read about. They do exist, but they are not in the scope of this course. An anomaly is an unintended consequence, something that happens to the data when we're doing something else to the data. We have update, delete, and insert anomalies to consider. And in all of these situations, we're doing something to the data. We're changing the data somehow in an expected way, but unfortunately it's causing an unexpected change to that data. That's the anomaly, is the unexpected change the unintended change made to the data. Now we have to talk about data, and it just makes our life easier to add some semantics to these examples to better understand the anomalies. I could do this with a type of logical design that I've already showed you. It just makes our life easier if we add some semantics. Here's the example we're going to use, and yes, I will be adding some semantics in just a moment, but this looks familiar to you. We've seen this notation before, and we will agree that we are not in 2NF. And the reason we are not in 2NF is because C determines D. C is a non-prime attribute, D is a non-prime attribute, therefore to be in 2NF, there cannot be any non-prime attributes determining other non-prime attributes, and that violates 2NF. The trick here, the thing to remember, is we're going to stop and use this as is. We're going to put data into this relation as is. We're not going to fix it. Okay, so we're agreeing that it's broken right now. It's usable. I mean, we could certainly make a database out of this, and we could store information in it, but we're opening ourselves up to some anomalies. And that's what we want to show, is the anomalies that will cause us problems if we don't normalize it to a greater extent. And here we go. I'm going to add some semantics. I'm going to change the column headings to useful real-world names, and I'm going to add some data. Get ready. Poof. Here's the same relation. I still called it R, but I added SSN as the A attribute, which is our candidate key, social security number, last name, salary, commission percentage. Again, as we go through this, do not stop and think about the semantics. Do not say, well, not everybody has a social security number, or sometimes the last name changes for a person. And yes, it certainly does in the real world, but just live with my semantics and live with my logical design. We're not going to debate the veracity of this logical design in the real world. It might not work for some purposes, but it is a logical design, and it is correct because I'm saying it's correct. That's the only reason it's correct, is because I have blessed it and I have decreed that it will work for whatever purpose it is supposed to work for. So don't overthink it, and don't try to impose more semantics on it. It'll just make you nuts. At the bottom of the slide, I have provided some data. And again, I don't have to provide data to demonstrate anomalies, but it just makes the understanding more effective for all of us. I provided 3 rows of data, 3 unique social security numbers, because that is the key value, 3 last names, 3 salaries, and then over on the end I provided something in the table called commission percentage, 3.711% on the Smith row, 4.711% on the Jones row, and 3.711% on the Miller row. Now, what does that number mean? Not a lot right now. It doesn't have a lot of context. All I know about commission percentage is that it is determined by salary, and it is not determined by anything else. Therefore, if I give you someone's social security number or someone's last name, you cannot tell me a commission percentage. You cannot tell me their commission percentage or any commission percentage. Does this table make sense? Hopefully it doesn't make sense to you. Hopefully you realize that that commission percentage column is a mess. Where did it come from? Why is it there? Well, the semantics seem to tell us that it shouldn't be there. And as a database designer, as a database analyst or a systems analyst, this will become second nature to you. You will begin to realize that, hey, that is in the wrong place. And then, because of the things you've done in this course, you will be able to realize that it is in the wrong place, and we can say it is a 2NF violation. So your intuition is explained by the formal terminology we use, and that is a 2NF violation. Imagine what would happen if this went to production in this form, and believe me, this has happened many times, and over time we accumulate rows and rows and rows of data and open ourselves up to tremendous data anomalies because that commission percentage is just out of place and shouldn't be there, frankly, under those circumstances. We will assume then that this database is in production. It has some data in it, and then in the following slides we will look at the anomalies that can arise. The first anomaly we will consider is the update anomaly, and that is when we change some data in a table. Let's just focus on a single row of the table. And remember, table and relation are the same, so I guess we kind of say that it's a relation in the logical design step, and it becomes a table in the physical implementation. That's a common way of looking at this, but we can call it a relation or a table. And something bad is going to happen, or something unintended is going to happen to that row when we make a legitimate update to that row. And let's look at the situation where we're going to change the first row. We're going to change information for Smith. And we decided that Smith will have a commission of $3.811, but Smith's salary is $120,000. And that's fine, but do we also need to change the commission for Miller? Because Miller had a salary of $120,000. And since salary determines commission, we know salary determines commission because it was one of the determinants that we were given in the logical design. We seem to have violated that determinant because salary no longer determines commission percentage. For Smith, salary is $120,000, commission is $3.811. For Miller, salary is also $120,000. However, commission is $3.711. So the salary no longer determines commission percentage. We have violated that functional dependency. We have violated the design that we gave ourselves. This is an update anomaly. And you may think, well, it's no problem. Let's just go through and change everybody that has a salary of $120,000 to the new commission percentage 3.811. And yes, we can certainly do that, but we're opening ourselves up to tremendous opportunities for error because we may forget to do that, or we may do it incorrectly. We may not be able to do it. We may only have access to one row in the table, and that's Smith. Therefore, this is an update anomaly, an unintended consequence of editing one row in the table. A delete anomaly is when we delete a row and we lose information that we otherwise should have kept. Now, when we delete a row, we understand what is supposed to happen. We delete by candidate key or some key, and we're losing all the information that key determines. But in this case, since we're only in 2NF, we're going to lose other things too, not determined by that key. And let's say that we're deleting Jones, the second row in the table. When we delete Jones, we delete his social security number, his last name, and his salary, which is fine because they're all determined by the candidate key, social security number. But we also delete commission percentage. So now we have no idea what the commission percentage is for someone making $130,000. It's gone. It's completely unavailable to us. That's the unintended consequence of deleting that row. And the reason that happens is because we deleted something that is not dependent on the candidate keys in that table. That's a delete anomaly. Now that's easy to do. Since we're not normalized, we don't think about it. We're not normalized to beyond 1NF, I guess. We don't think about it. We delete the row. We delete what we think is the information about one person, but we're also deleting things that are not directly related to the person, and we're in big trouble. The third type of anomaly is an insert anomaly, adding data to a table. Well, you think that would, nothing could go wrong there, right? We're creating new data, putting it in a table, but we're creating more problems for ourselves because we may not know the values to add in all of the attributes, since some of the values we're adding are not determined by all the candidate keys. I've added a row to our data set. I have Smith, Jones, and Miller. I've added Cheney. Cheney's social security number is unique, as it should be, because it's the candidate key, no problem. Cheney's last name is there. Cheney's salary is there. Those are things that we would expect to know before adding this row to the table. We would expect to know the person's social security number. We would expect to know their last name. We would expect to know their salary. Those are reasonable. But why should we know their commission percentage? That should probably come from somewhere else, because Mr. Cheney can give me his SSN, his last name, his salary, but he can't give me his commission percentage. He doesn't know what that is. That's not on his application for the job. And since it's determined by his commission, by his salary, we don't know it. And we might not be able to add that row at all if the table is designed such that commission percentage cannot be blank. Or we might just make it up out of thin air because we don't know what it is, and that's even more of a disaster because Cheney would not be paid correctly. Therefore, this is an anomaly of the data because we don't know that information when we go to add that row to the table. So we've seen three types of anomalies that can occur when a table or relation is not in 2NF. And we could extend this to 3NF and do the same types of examples. I encourage you to do that on your own. I would also encourage you to normalize this logical design to 2NF. In other words, break out that commission percentage into a separate table and then apply these three anomalies again to the two tables that you created and see if these anomalies still exist. Are there still insert, update, and delete anomalies if we take this logical design to 2NF? It's an excellent exercise for you to see if you understand all the concepts that we've covered. Thank you.